Good afternoon and welcome to today's Maritime Innovation Update. I am Pascal Hohnrath. I am working as a research associate at Fraunhofer CML. Today I have the pleasure to moderate my colleague Cosmin Delea's presentation with the title of Hunters and Gatherers, Marine Litter Datasets. Cosmin is also a research associate at Fraunhofer CML. His research focuses on control and perception of unmanned systems. He's the project manager of the SeaClear 2.0 project, in which a robotic solution for collecting marine debris is developed. Today's presentation showcases some of the findings in the area of marine litter detection. Please turn off your microphones and cameras during the presentation. Feel free to post questions in the chat. There will be a short Q&A session after the presentation. And now, without further ado, Cosmin Delea, the stage is yours.
Thank you very much, Pascal, and hello, everyone. First of all, can you hear me well? Is the sound clear enough? Yeah, okay, thank you very much. So welcome, everyone. Today we're going to talk about marine litter datasets. And the short lesson for today is grouped into three chapters, three main points. First, we're going to talk about the SeaClear 2.0 project as a whole, and then we're going to jump into marine litter composition, preparation for the later point, which is the dataset creation and upscaling solution. Without further ado, let's look into the project. So SeaClear 2.0 project is an extension of the first project, SeaClear 1.0, that ended up last year. You can see the first system on the right-hand side of the screen, of the picture on the screen. Essentially, both systems are composed of various unmanned vehicles that have the purpose of finding and collecting marine debris. The SeaClear 2.0 system is composed of central unmanned surface vehicle, which we call it SeaClear 2.0, that launches one underwater vehicle for mapping and mapping the marine litter and detecting it, and another unmanned vehicle for grabbing or collecting the marine debris. For the transportation to shore and ensuring continuous operation of the system, we have a secondary USV, which we call a tender, which is capable of loading about 350 kilograms of litter. Now, the approach of the SeaClear 2 project involves several steps. Not all of them being.
Cosmin, can
yes.
I shortly interrupt? You are not sharing the presentation.
I'm sorry, I don't know what happened.
No worries.
I'll try again. Thank you. Is it now better?
Yes, we can see it now. Thanks.
Okay. Thank you very much. So I don't know if you saw the previous slide. I'll go back for a second. So this is the picture I was referring to beforehand. The system is composed of several unmanned surface vehicles that you see on the screen, and also a couple of unmanned underwater vehicles. Now, the approach of the SeaClear 2 project is composed of several steps, not all of them being technical. Some of them are focused also on the public engagement on policy recommendations for cycling up the marine litter. We also look into the full cycle of the marine litter handling, and we aim to demonstrate the robotic solution through 3 demonstration and 3 pilot tests. And referring now to the tests themselves, we have here a map of the coastal areas that have been, I don't want to use the word certified, but marked as areas where marine litter zones have been found. These are marked with the red dots. From this Mediterranean basin, we chose 5 locations based also on the partners that we had, of course, available. And 3 of them will be demonstrations where the Cicely 2 system will be demonstrated, and other 2 plus Hamburg will be the test sites where part of the system will be tested. Now, jumping into the problem of marine litter now, we have done an analysis, first of all, to understand the problem that we're tackling. And the results are shown in the 2 graphs, some of the results, of course. So we looked into various sources and found out that there are multiple marine litter fractions to be found. In order to group them, we settled upon size grid or volume, let's say. This is the one displayed on the left-hand side of the screen. And as you can see, there are certain sizes that are much more common. Why is this important? Because we wanted to create a system that can grasp certain marine litter elements. Therefore, we need to know what kind of volume do we have to grasp. On the right-hand side, you find some specific findings from the test areas regarding the number of items that were found per square kilometer. These are also from public sources as well as info that we have received during the analysis of the test sites. And the key takeaways of this overview are that we, in the test site and demo site that we have presented, we have an average density of around 325 items per square kilometers, where we have large variations in some test sites. So it really matters where exactly do we put do we survey itself, we do the survey itself. We have great densities in the eastern part of the Mediterranean Sea. In the Hamburg use case, in the Hamburg test site, we have a very specific use case because there is a river flowing in, and therefore the litter that is not accumulated here, so it gets transported further. So getting data from Hamburg itself, it really varies by the season when we do the probing. Yeah, a bit about the system. So we settled upon the following specifications of the system, of the robotic solution, so that we become relevant for the problem that we just discussed earlier. Most important from this, most important items from this list for the marine litter composition are the last 2 elements. So we aim for a 350 kilogram payload in the tender USV where we're going to collect the litter, and each element that will be picked up will have a payload of up to 105 kilograms with some inbuilt buffer. The operational volume, so the sizes of the collected litter are approximately 100 by 100 by 100 centimeters, so 1 meter by 1 meter. These are the elements that will be picked up in the demo and by the test sites. Now, going into the data set itself, because this was the main point of our discussion today, we looked into several options for using this machine learning models to train upon data sets. But having the data sets is also a very crucial point, because without good data, there's no good training. Without a good training, there's no good validation. Without good validation, there are no real good results. Therefore, we found a public cloud solution to scale up our data set. Now, I'll go a bit into the process of doing the data, of creating this data set, and I'll first explain the workflow in this cloud solution that we picked up. The cloud solution itself is from Microsoft Azure Cloud, and first, we use the storage account tool for dumping the data of structured and then unstructured. Then within the machine learning workspace, we can label the material and train the pre-selected model. The labeling can also be done automatically, or let's say assisted at from around 10%, after 10% of the material has been manually labeled. Training sessions can be booked on cloud computers, and specific performance can be selected for the training. Lastly, inside the Vision Studio, the performance of the trained machine learning model can be assessed by selecting a validation data set. There are also other possibilities for integration with external interfaces, but I'm not going to go to these topics right now. For the data set that we have collected in Hamburg, we have conducted around 9 test campaigns, so data collection campaigns, in which 8 categories of litter have been found or have been placed for assessment. We have sorted just around 2,600 images and labeled them using the COCO annotation format, and we grouped them into training and evaluation data sets, and we booked over 100 plus training hours. Now, this is just the beginning, because the data set will grow eventually and will cover up all the other tests and demo sites. These are some pictures of the data from the data that we acquired. There are typical elements found as we also discussed earlier. There are very classical categories of marine litter that can be used for classification, and all the data that we got here was respecting the nomenclature that we established earlier. Very classical example, the tire is probably found everywhere, especially in port areas. We have plastic bottles like everywhere, and also on the lower row you see bicycles and e-scooters, which is much more of a, I would say, unfortunate result or effect of the modern transportation methods or means of transportation that we have nowadays. Some of the public bikes and e-scooters end up in rivers, and that's really a pity, and we have to do something to get them out. The pictures that you see on the right-hand side in the lower right screen are e-scooters that have been found already in the Elbe River, so we have not thrown any e-scooters in the Elbe River, just for this disclaimer. Okay, and for the bicycle, I chose the bicycle to show you how the labeling can be done within the Azure cloud. It's relatively straightforward. Once you have the data curated or correctly structured in your data storage, you can pretty much go ahead and manually select the bounding box for annotating this picture. And on the right-hand side, you see how the bicycle looks on the sonar image. The picture was taken with 1,200 megahertz frequency, and a human can easily identify the two wheels. Maybe the chassis is a bit more difficult. The chain can also be a bit identified, but all in all, the picture that you see on the right-hand side is really a good one for a bicycle, meaning that we can identify several features. Lastly, I would like to show you the last step, because I talked about cloud solutions. So the idea that I'm trying to showcase here is that all the solutions that you have seen in this presentation can be done without having any application installed on your computers. Hence, the process of viewing the data set or even annotation can be done from a low power computer or even a tablet, for example. The most interesting is to use these solutions for evaluating the performance of your machine learning model, and that can also be done really easily, and I will show it in the following video. So essentially, the user here goes into the Vision Studio and tries out the already trained model with different pictures that he or she has available on them from the test site or directly from a new data set, for example. And as you can see, the performance is really good because the training data set that we have used was covering pretty much many angles or many orientations of the images. Therefore, the test images that we used in this video were scored or evaluated with a pretty high accuracy, over 90%. Yeah, and I think this repeats. So what are the takeaways of today? We have discussed about the Secret 2 project, which tackles the problem of detecting, mapping, classification, and removing marine litter in ports and coastal areas. We focused, of course, on the detection part today. For establishing a data set, a marine litter composition and occurrence analysis has to be done for the test size that one has envisioned. And consequently, a data set from the test site has to be gathered in order to train on the machine learning models with relevant information. And lastly, a cloud-based solution is ultimately needed for hosting the cloud infrastructure if you want to upscale your solution so that the multiple developers from different test sites can contribute and enhance the performance or just maybe collect more data. With this closing remarks, I would like to thank you for your attention. Feel free to contact me in case you have further questions. This is my contact information, and looking forward for your questions if there are any.
Yeah, thank you very much, Cosmin. Since there are no questions in the chat yet, I would like to ask a question myself. I was wondering, how would the process look like if we had to combine cameras and sonar for acquiring a data set?
Yeah, that's correct. We didn't touch on the camera because this is probably something that many people are interested in. So the process shown here is focused on the Hamburg port use case, where camera usage, I would not say it's meaningless, but it's relatively difficult to find some relevant information from cameras, unless you have very, very, very high quality images with very performant lighting conditions. Now, if you were to use cameras alongside sonar data, you would actually need a second pipeline in which a separate machine learning model is trained on camera data, and you would need correspondingly a different data set and a different storage for it. A storage container, to be more specifically, if we speak of Azure Cloud. But all in all, you could really pretty much repeat the same process of gathering material, sorting it, labeling, and then trying it out. You would just have to select the right model. This will be for the training part. Now, for deployment, you would need to have some kind of a higher level controller that takes in both outputs from both systems, and you would need to have also the sensors themselves calibrated, so you would know exactly what's the distance between the physical positions of the sensors on your vehicle, so that you can know whether the detected image from the sonar is the same as the one detected by the camera or the element itself, if they are referring to the exact same element. So these would be the two main changes, I would say. Of course, it's easy to just say them, but it's really more difficult to implement it itself.
Yeah, thank you for your answer. Very interesting. I will have a final look in the chat. There are no further questions. So I would like to thank you for your attention. Finally, I would like to draw your attention to next week's presentation, which is about the data situation for inland waterway infrastructure. Please be aware that this presentation will be in German. Yeah, thank you very much again, and have a nice weekend.
Thank you very much as well. Have a nice weekend.